This is my geometry course. Today we're going to continue to learn proofs and properties of equality and congruence. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the last two classes, we learned how to show statements are true with two-column proofs. We're going to continue to do that in this class, but we're specifically going to prove the Right Angle Congruence Theorem, the Congruent Supplements Theorem, the Congruent Complements Theorem, and we're also going to study the concept of, we're going to show what perpendicular means, the word perpendicular. But before we go forward, I'm going to show you a screenshot of all the postulates and theorems that we have learned so far, just so you can keep that in your files in case you do forget one of those postulates or theorems that we may need to use. So that said, let's get started. Again, we're just proving statements. So we're going to prove the following statements with two-column proofs. And the first statement is what we call the Right Angle Congruence Theorem. That's this statement here. If angle A and angle B are both right angles, then they are congruent. Again, that statement is called the Right Angle Congruence Theorem. So we're going to prove that right now. Now you might be thinking to yourself, wait a second, this theorem seems kind of stupid. Why in the world would we need to prove this? If two angles are both right angles, then obviously they're congruent. Well, that is true. It is an obvious statement. We don't really need to prove it, but remember in geometry class, sometimes you do need to prove things that seem to be obvious. And the reason that we're going to prove this statement is that we can use this theorem when we do other proofs, and it's going to allow us to skip steps when we do those other proofs. So let's get started. We'll begin with the given information. Angle A and angle B are right angles, and that's given. By definition, if they're right angles, then the measure of angle A must be 90 degrees, and the measure of angle B must also be 90 degrees. And that is the definition of right angles. Now, if the measure of angle A is 90 and the measure of angle B is also 90, if they're both equal to 90, then that means by the transitive property of equality, they must be equal to themselves. So the measure of angle A must be equal to the measure of angle B by the transitive property of equality. Now, if the measures are equal, then by definition, the angles themselves must be congruent. And that's what we were trying to prove, that if angle A and angle B are both right angles, then they are congruent. And that is the definition of congruent angles. So, like I said, we're going to make a theorem out of that. At the bottom of the screen, you can see that theorem. If two angles are both right angles, then they are congruent. You may see that theorem stated a little differently. You may hear it as right angles are congruent. You may see a more condensed form of that statement. All right, so again, I know that seems pretty obvious, but we're going to use that in other proofs. It's going to make other proofs easier, fewer steps. So now I want you to prove a very similar statement. If angle A and angle B are both straight angles, then they are congruent. Now remember, a straight angle is an angle whose measure is 180 degrees. That's just the definition of a straight angle. Now I want you to go ahead and take a screenshot of this problem that we just did, and that's going to help you with this problem. I want you to do this problem on your own. It's going to be almost exactly the same as the problem we just did, but now we're dealing with straight angles. So go ahead and try to prove this statement, and when you come back, we'll do it together. All right, we're back. We'll start with the given information. Angle A and angle B are straight angles. And that is given information. Now, if they're straight angles, then by definition, the measure of angle A must be 180 degrees, and the measure of angle B must be 180 degrees. And that's the definition of straight angles. So now you can see measure of A and measure of B are both equal to 180 degrees. So that means by the transitive property of equality, they must be equal to themselves. Measure of A is equal to measure of angle B by the transitive property of equality. And by definition, angle A must be congruent to angle B. Definition of congruent angles. All right, so if that was your answer, good job. As you can see, it's almost exactly the same as the problem we did before. Now, you might say, well, where's the theorem? We have the right angle congruence theorem up here. Do we have a straight angle congruence theorem? Well, you could write a straight angle congruence theorem, but for some reason textbooks just don't really, they don't have a name for that statement. You may find one on the internet somewhere, but they just don't really use it much in proofs. So I guess they don't have a special name for that, so you don't have to worry about a special name for that. All right, so we're now going to use the right angle congruence theorem to do other proofs, and you're going to see that it's going to allow us to skip steps if we can use that theorem. But first, in order to go on to these next problems, like I said, one of the things we're going to study today is perpendicular, what the word perpendicular means. So this is a definition. Perpendicular lines, we're going to start out with lines. You can have perpendicular segments or perpendicular rays or perpendicular lines, but we're going to start out with lines. If two lines are perpendicular, and again, perpendicular is an adjective, so if two lines are perpendicular, then that means they intersect to form right angles. So let's say you have two lines that intersect, and the angles between them are all 90-degree angles. Then, and that's something that I don't think I went over. I can't remember if I went over that yet, but when you write a 90-degree angle, you can write a box. That means 90 degrees. So we're going to do that today. But again, if these lines are perpendicular lines, that means that this angle, all of the angles must be 90 degrees. This angle and so on and so forth. But you can notate a 90-degree angle with a box. That's just universally recognized pretty much as a 90-degree angle. So we're going to need that idea of perpendicular to go on to the next proof here. All right, so if segment AB and segment BD are perpendicular, so what that means is we have AB here and we have BD here, and they're perpendicular. So what that means is this angle is 90. That's all that means, is 90 degrees. And you can actually write a box there if you want to remember that. So this angle is 90 degrees. That's what that means. So if these are perpendicular, let me get a color that'll stand out there. If these two segments are perpendicular, and AC and CD, segment AC and segment CD are also perpendicular, so AC is here and CD is here. These are also perpendicular, meaning that's a 90-degree angle. Then angle ABD, and angle ACD are congruent. Now let me go over that one more time just so you understand exactly what's going on here. So this segment is perpendicular to this segment, which means that this is 90, and this segment is perpendicular to this segment, which means that this is 90. So therefore, these two angles are congruent. That's what we're trying to prove. Now I'm going to do this one for you, and you're going to do a similar problem for number 4. So don't worry about doing this problem right now on your own. But I want you to understand that I'm going to prove this statement without the right angle congruence theorem, which is what we just learned. I'm going to prove it without using this theorem. Then I'm going to prove it with the theorem. And you're going to see that we're going to use fewer steps because of that theorem. So it's going to help us jump over some steps. So anyway, let's prove it without the right angle congruence theorem. So I'll start out with the given information. AB is perpendicular to BD. Now, we're going to use some shorthand notation to show the characteristic perpendicular. We're going to use this symbol right here. You see that? That means perpendicular. You haven't seen that before in this class or this course. AB is perpendicular to BD. So you're going to need to remember that symbol. That means perpendicular. We're later on going to learn the concept of parallel. You've probably heard that word before. Parallel, the symbol parallel is just two lines, but we're not going to learn that today. We're going to learn that in some subsequent classes. So AB is perpendicular to BD, and we also know that AC is perpendicular to CD. That's given information. Now, if they're perpendicular, then by definition, angle ABD and angle ACD are right angles. So again, that's just the definition of perpendicular. If this is true, if these are perpendicular, then the angles formed by the intersection of those segments must be right angles. So I think that's right. Right, and that is the definition of perpendicular. All right, so now we're trying to show, just to go back and make sure you understand what's going on here, we're trying to show that these angles are congruent. So we've already proven that they're right angles. So angle ABD, we know it's a right angle. So the measure of angle ABD must be equal to 90 degrees. And the measure of angle ACD, that must be equal to 90 degrees also. So I'm going to reorganize this a little bit. I'm going to move that over and move this over. There we go. Sorry about that. So measure of ABD is 90 degrees and measure of ACD is 90 degrees. So now you can see where we're going with this. If both those angles are 90 degrees, then they're obviously, the measures are equal to each other by the transitive property of equality. Let's see here. We need to say definition of right angles. And this is the transitive property of equality. And then, of course, by definition, angle ABD must be congruent to angle ACD. Definition of congruent angles. And that's what we were trying to prove. Measure of our angle ABD and angle ACD are congruent. Now, we did not use the right angle congruence theorem. You see, at this point, we know that they're right angles. So if we used the right angle congruence theorem, we could have just gone to the very last step and skipped these two steps. So now we're going to use the right angle congruence theorem, and you're going to see that we're going to be able to skip those two steps. So what I'm going to do is I'm just going to copy this because it's, actually I'm going to copy the first two steps because they're exactly the same. All right, so now At this point, we know that they are both right angles, right? So because they're both right angles, we can immediately skip those two steps we did before and say that they're congruent. And we know that right angles are congruent. Because they're right angles, we know that they are congruent by the right, I'm just going to spell it out, Right Angle Congruence Theorem. All right. So as you can see, by using that simple theorem, we were able to skip two steps. We skipped these two steps here. So that's why we're learning these very simple theorems. All right, so now I want you to try a similar problem, but before you try that problem, go ahead and take a screenshot of these, of number 3. So you can see the proof without the right angle congruence theorem, and you can see it with the right angle congruence theorem. Now you're going to do a very, very similar proof. Very, very similar. You're going to prove it without the right angle congruence theorem and then with the right angle congruence theorem. So go ahead and try to prove this statement without the right angle congruence theorem. If BE is perpendicular to DE, so this line is perpendicular to this line, if that's true, and we also know that ABC is a right angle. You see this little box here? That means it's a right angle. So ABC, this angle over here, is a right angle. So we know this line is perpendicular to this line, and we know that this angle is a right angle. Then angle ABC, this angle, must be congruent to this angle here, DEB. So that's what we're trying to prove. So again, I just want to make sure that you understand what's going on here. We know that this line and this line are perpendicular. So that means that all these angles are 90, you see. They're all 90 degrees. They're all right angles because that's the definition of perpendicular. It means that the intersection forms right angles, meaning these are all 90 degrees. And we are also told that this is a right angle, which means that this is 90 degrees. So if we know that all these are 90 degrees, and specifically we know that angle DEB is 90 degrees because that's the one we care about, and we know that this is 90 degrees, then obviously they're congruent. You have to prove that. So, but again, you're not allowed to use the right angle congruence theorem. We're going to do that in the next proof. So try number 4, and when you come back, we'll do it together. All right, we're back. So we'll start out with the given information. Line BE is perpendicular to line DE. That is given. Now we know that angle BED, or excuse me, we should say DEB. It's the same angle, but we should keep it the same order. I don't want to confuse you. Angle DEB is a right angle, and that's just the definition of perpendicular. Because these lines are perpendicular, we know that that angle, because these lines are perpendicular, we know that this angle must be a right angle, because that's the definition of perpendicular. So now, by definition, we know that, let's see here. I think I'm going to go to the other given information first. It doesn't, you can do things in a slightly different order. You don't have to show every step in the exact order I'm doing it. But I think I'm going to go to angle ABC is a right angle. That's given information. That was the other given information that we have. All right. Now at this point, if we were going to use the right angle congruence theorem, we could just say that these two angles are congruent and we'd be done. But we're not using the right angle congruence theorem. We're trying to see what it's like without using the theorem. So now we're going to say that DEB is equal to 90 degrees. And we also know that, whoops, that should be measure. Measure of angle DEB is 90 degrees, and the measure of angle ABC is also 90 degrees. And that's just the definition of right angles. So now we can say that the measure of angle ABC is equal to the measure of angle DEB. And because they're both equal to 90, that's true. That is the transitive property of equality. And by definition, angle ABC must be congruent to angle DEB. Definition of congruent angles. And it looks like we didn't need those last steps. So that was the proof of that statement. We did 6 steps. So if you got that answer, good job. And again, you may have written these steps in a slightly different order. That's okay. And you may have done 2 separate steps for this. You may have broken it up into 2 steps. That's okay also. But now I want you to prove the same statement, except now we're going to use the right angle congruence theorem. So go ahead and try that, and you're going to see that you're able to skip 2 steps. Here we did 6 steps, but here we're only going to do 4. So try this proof, and when you come back, we'll do it together. All right, we're back. So the first 3 steps are going to be pretty much the same. So I'm going to copy that. Now at this point, we know that these 2 angles are right angles. So because we know that they're right angles, we can just say that they're congruent. So angle ABC is congruent to angle DEB. And that is the right angle congruence theorem. Now again, that's the theorem up here we proved, right angle congruence theorem. So if you got that answer, good job. As you can see, we skipped 2 steps. Once you know that 2 angles are right angles, you can say that they're congruent by the right angle congruence theorem, but you do have to state that theorem as a reason for that logic. All right, now we're going to go on to something a little different here. We are now going to prove something called the Congruent Supplements Theorem. This is another theorem that's going to help us to skip steps in other proofs. So I'm going to prove the Congruent Supplements Theorem, and then you are going to prove what's called the Congruent Complements Theorem. So let's start with the Congruent Supplements Theorem. Angle A, first of all, let's read it. If angle A and angle B are supplementary to angle C, then angle A is congruent to angle B. That's actually kind of a confusing statement there. Let me just be sure that you know what that means, because again, this is kind of confusing. So you have angle A, right? And you have angle B. What this is saying is that they're both supplementary to angle C. Now, if you forgot what supplementary means, that means the sum of these 2 angles is 180 degrees. The sum of their measures is 180 degrees. And the sum of the measures of these angles is 180 degrees. So if you add these up, you get 180, and if you add these up, you get 180. So as you can imagine, these 2 angles must be equal. The measures must be equal. That's what the theorem is saying. If these are supplementary and if these are supplementary, that means that these 2 angles are equal. Very important to understand what exactly the statement is saying. It's kind of confusing. We're going to prove that that's true. And again, this is called the Congruent Supplements Theorem. So we haven't proven it yet, though. So angle A is supplementary to angle C. And angle B is also supplementary to angle C. That's what that's saying. That's given information. Again, I know that's kind of confusing, but that's what the statement is saying. Now, if that's true, if angle A is supplementary to angle C, then by definition, the measure of angle A plus the measure of angle C has to be 180 degrees. That's just the definition of supplementary. And we also know that the measure of angle B plus the measure of angle C must be 180 degrees. Because again, A is supplementary to C, but it tells us that B is also supplementary to C. So that is the definition of supplementary angles. Now you can see what's going to happen here because we have two things that are both equal to 180, they must be equal to themselves. So measure of angle A plus measure of angle C is equal to measure of angle B plus measure of angle C. Transitive property of equality. Now you can see what's going to happen here. We have C's on both sides. So we're going to subtract out these C's. So measure of angle A is equal to measure of angle B by the subtraction property of equality. So we just subtracted measure of angle C from both sides. And of course, by definition, angle A is congruent to angle B. Definition of congruent angles. So we proved the Congruent Supplements Theorem. So that's this theorem down here. Now I want you to prove a very similar theorem, the Congruent Complements Theorem. So go ahead and take a screenshot of this because you're going to, you can refer back to it when you're proving the next theorem. So I want you to prove this theorem, and I'll just leave this in the window, I guess. Prove the Congruent Complements Theorem. It's almost the exact same statement, except now you're talking about complementary angles. Now, complementary means that two angles add up to 90. So we have angle A and angle B, and they're both complementary to angle C. So that means if you add these up, the measures of these, you get 90, and if you add the measures of these, you get 90. So if that's true, then these two angles must be congruent. So it's kind of the same thing. It's just now we're talking about complementary angles. Supplementary angles add up to 90, or excuse me, supplementary angles add up to 180, and complementary angles add up to 90. So go ahead and prove, do number 6, do a 2-column proof for number 6, and when you come back, we'll do it together. All right, we're back. We'll start with the given information. Angle A is complementary to angle C, and angle B is also complementary to angle C. And that is given information. Now, if angle A and angle C are complementary, then the measure of angle A plus the measure of angle C must be 90 degrees. That's just a definition. And if angle B is complementary to angle C, then the measure of angle B plus the measure of angle C must also be 90 degrees. That's definition of complementary angles. Now, you can see where we're going with here. It's just another example of the transitive property of equality. If these are both equal to 90, then they must be equal to themselves. So that is the transitive property of equality. Subtract measure of angle C from both sides, and we get measure of angle A is equal to measure of angle B. Subtraction property of equality. And then obviously angle A must be congruent to angle B, and that is just the definition of congruent angles. So if you got those answers, good job. And again, that is the Congruent Complements Theorem. So if you haven't done this already, I want you to go ahead and take a screenshot of these theorems just for this class today. Now again, I'm going to give you a list of all the postulates and theorems that we've learned so far in this class. So don't be too nervous about having to keep a record of all this, because I'm going to keep a record for you. All right, so now that we've learned the Congruent Supplements Theorem and the Congruent Complements Theorem, we're going to use those theorems in some problems. Now, I'm going to do number 7 for you, and then you're going to do number 8 on your own. We're going to do a proof without the Congruent Supplements Theorem, and then we're going to do the same proof with the Congruent Supplements Theorem. Now, this is an important proof because this is the Vertical Angles Theorem. The Vertical Angles Theorem tells us that all vertical angles, the vertical angles are congruent. So these are vertical angles because they're right across from each other. Remember, they're also called opposite angles. Sometimes it's called the Opposite Angles Theorem, but we've called it the Vertical Angles Theorem. These two angles are across from each other. When two lines intersect each other, they make 4 angles, and the ones across from each other are congruent, and these are also congruent, but we're just going to prove that 1 and 3 are congruent. And that's going to be the proof of the Vertical Angles Theorem. Now, we introduced the theorem, but we didn't prove it. Now we're going to prove it. And again, we're going to prove it without the Congruent Supplements Theorem. So we'll start out with the given information. We can see by the diagram that angle 1 and angle 3 are vertical angles. That's given information. It's given in the diagram. Now, we can see that angle 1 and angle 2 are supplementary, we can see that they're a linear pair. Angle 1 and angle 2 are adjacent angles whose non-common sides, this side and this side, are opposite rays. That's just a fancy way of saying that these two angles, when you put them together, when you make them adjacent angles, they add up to 180 degrees. They make a straight angle. So this one plus this one make a straight line. So angle 1 and angle 2 form a linear pair. But it's also true that angle 2 and angle 3 form a linear pair. Do you see that? So these two angles form a linear pair, but these two angles form a linear pair also. So angle 2 and angle 3 form a linear pair. And we can see that that's just given in the diagram. Now, remember the linear pair postulate. If two angles form a linear pair, then they are supplementary. So angle 1 and angle 2 are supplementary angles. And we also know that angle 2 and angle 3 are supplementary angles because they form a linear pair also. Now that is the linear pair postulate. All right, so by definition, if angle 1 and angle 2 if they're supplementary, then remember the definition of supplementary is that their measures must add up to 180 degrees. So measure of angle 1 plus measure of angle 2 must be 180 degrees, and measure of angle 2 and measure of angle 3, they must add up to 180 degrees. That is the definition of supplementary angles. So you can see where we're going with this. We have two things that are both equal to 180 degrees, so we can use the transitive property of equality to show that they're equal to themselves. So now you can see we have measure of angle 2 on both sides. So we're going to subtract measure of angle 2, and we get measure of angle 1 is equal to measure of angle 3. And that is the subtraction property of equality. And then we can just say angle 1 is congruent to angle 3 by the definition of congruent angles. So we used 7 steps to prove the vertical angles theorem. So now we're going to prove the same theorem, but we're going to use the congruent supplements theorem. And it looks like the first 3 steps are going to be the same, so I'm just going to copy that. And I'm going to put it up here. So you can see we have most of the work already done. It's pretty much the same thing. But let me see, let's move this up a little bit. All right, so we're at the step where we've shown that angle 1 and angle 2 are supplementary angles. And let me highlight that. Angle 1 and angle 2 are supplementary angles. And we also know that angle 2 and angle 3 are supplementary angles. So we're going to use the Congruent Supplements Theorem. So let me explain exactly what's going on here. Angle 1 is supplementary to angle 2, but angle 3 is also supplementary to angle 2. Very important to understand what's going on here. I want to say that again. Angle 1 is supplementary to angle 2, and angle 3 is also supplementary to angle 2. All right, so we have 2 angles. I'm sorry, I don't know why it keeps doing that. We have 2 angles, angle 1 and angle 3, that are both supplementary to the same angle, angle 2. So because they're supplementary to the same angle, they must be congruent. That's the Congruent Supplements Theorem. Again, we're skipping steps here because we're using the Congruent Supplements Theorem. So because angle 3 and angle 1 are both supplementary to the same angle, they must be congruent. We can just jump to that statement. Angle 1 is congruent to angle 3 because we can use the Congruent Supplements Theorem. So by using that theorem, it allowed us to skip, let's see how many steps. Here we had 7 steps, and here we had only 4 steps. So you can see that the Congruent Supplements Theorem really helps us to do proofs more quickly. All right, so you're going to do a very similar proof. You're going to do it without the Congruent Supplements Theorem, and you're going to do it with the Congruent Supplements Theorem. And again, be sure that you get a screenshot of number 7. That'll help you to do number 8. So let's come up with a game plan here. If angle 2 and angle 4 below are supplementary, then the measure of angle 2 is equal to the measure of angle 3. I want to help you with the general concepts before you start with this. So angle, you're gonna need to use the you're gonna need to recognize that these two angles form a linear pair. If these two angles form a linear pair, then that means that they are supplementary, and that means the sum of these angles is 180 degrees. Now we're given the information that this angle and this angle are supplementary, so that means they add up to 180 degrees. And by that, you're going to be able to prove that angle 2 is equal to angle 3. Now you're not going to use the Congruent Supplements Theorem, because if you know that these are supplementary, so if you know that angle 3 is supplementary to angle 4, and angle 2 is also supplementary to angle 4, then you know that the measure of angle 2 is equal to the measure of angle 3, or they're congruent by the Congruent Supplements Theorem, but you're not going to use that. You're going to use the Congruent Supplements Theorem in the second version of this proof. So you have to do it without the Congruent Supplements Theorem. Now in this particular proof, I would start out with the information that these two angles form a linear pair and go with that. We don't care that these two angles form a linear pair. We just want to stick with angle 2, 3, and 4. So in this case, angle 1 is not even really necessary. So sometimes you're given information, or you're given things to kind of to distract you in problems. Just be aware of that. So I would start out with these two angles form a linear pair and use the linear pair postulate. And this is a little harder proof today, but see if you can do it. Try your best. And again, we're starting out with information that is not necessarily given. Well, it's given in the diagram, but sometimes you don't always start out with the information that's immediately given in the sentence. So just be aware of that. So try number 8. You can do it in different ways. If you don't want to start out with this information, you don't have to, but that's the way I would do it. So try number 8, and when you come back, we'll do it together. All right, we're back. So angle 3 and angle 4 form a linear pair, and that's given. We can just see that in the diagram. Now we know that the measure of angle 3, actually we know that angle 3 and angle 4 are supplementary angles, and that's the linear pair postulate. And we know that and again, you can do this in a different, doesn't have to be the exact same order, but the measure of angle 3 plus the measure of angle 4 must be 180 degrees. And that is the definition of supplementary angles. Now, we're also told that angle 2, this is the given information in the sentence, angle 2 and angle 4 are supplementary angles, and that is given. And of course, we know by definition the measures of those angles, they must add up to 180 degrees. That's the definition of supplementary angles. And so now you can see what's going to happen. These two expressions are both equal to 180 degrees. So therefore, they must be equal to themselves. So the measure of angle 3 plus the measure of angle 4 is equal to the measure of angle 2 plus the measure of angle 4. Transitive property of equality. And now we're going to subtract measure of angle 4 from both sides, and we get measure of angle 3 is equal to the measure of angle 2, and that is the subtraction property of equality. And we're done. So if you got that answer, good job. That is the proof of that statement without the congruent supplements theorem. But now I want you to use, and if you got stuck on that, that's okay. That was kind of a harder theorem. But when you use the congruent supplements theorem, you're going to take this information and this information, and you're going to skip. You're going to skip right down to the final statement. Because if angle 3 and angle 2 are both supplementary to the same angle, namely angle 4, then that means they must be congruent. So that's going to help you skip a number of steps. So now I want you to try the same proof, except now you're going to use the congruent supplements theorem. So try this proof over here, and when you come back, we'll do it together. All right, we're back. So I'm going to take these first two steps, and I'm just going to copy them. So I've got those there. And then I'm going to copy step number 4. I'm just going to write it out, though. So we're given the information that angle 2 and angle 4 are supplementary. That's given. So now at this point, we know that angle 3 and angle 4 are supplementary angles because they form a linear pair. And by the linear pair postulate, they must be supplementary. So angle 3 and angle 4 are supplementary angles. But we were also given the information that angle 2 and angle 4 are supplementary. So because angle 3 and angle 2 are both supplementary to the same angle, that means they must be congruent. So angle 2 must be congruent to angle 3. That's the congruent supplements theorem. That's the theorem that we proved over here. You should have a screenshot of that theorem. So we're almost done. We're not quite done yet because we haven't shown that the measures are equal. We're not trying to show that they're congruent. We're trying to show that the measures are equal. So now we just do one more step. The measure of angle 2 is equal to the measure of angle 3. Whoops. I didn't say congruent supplements theorem. You got to actually write that statement there. So we jumped from here to here by the congruent supplements theorem. And now we can say the measures are equal by the definition of congruent angles. So you can see that we skipped. We had 7 steps over here, and we only had 5 here. So we're able to skip 2 steps. So if you got that, if you did that proof, good job. And again, if you get stuck in these, that's okay. These are proofs. It's normal to get stuck. If you get stuck, that's okay, but you need to understand the general idea of what we're doing because you are going to be expected to do proofs like this in this course as we go along. So now we're going on to the last 2 problems. Now we talked about the definition of perpendicular today, and we're just going to finish out 2 more problems that give us a little more experience with the concept of perpendicular lines. So in previous problems, we were told that 2 lines are perpendicular, and then we could conclude from that the angles formed by those lines are right angles. But now we're going to kind of go in the opposite direction. We're told that we have a right angle, and that's going to somehow prove that lines are perpendicular. So we're trying to prove that lines are perpendicular. In order to do that, we have to show that the angles formed by those lines are right angles. So I'm going to do number 9, and then you can do number 10. All right, so let's read this. The measure of angle ABC is equal to the measure of angle 2. So this angle is equal to this angle. And we also know that angle 3 is a right angle. We know that this is a right angle. So if all that's true, we have to prove that line AB is perpendicular to line BC. So let's see if we can come up with a game plan here. We're told that this is a right angle, right? If that's a right angle, then it means it's 90 degrees. Now, you see these lines intersect, which means that angle 3 and angle 2 are vertical angles. Now we know that all vertical angles are congruent, so if this is 90 degrees, it's a right angle, it's 90 degrees, that must mean that 2 is 90 degrees also. Now we're told that angle 2 is equal to angle ABC. So if angle 2 is 90 degrees, that means ABC is also 90 degrees. Now if angle ABC is 90 degrees, that means it's a right angle. And if it's a right angle, then by definition, these lines AB and BC must be perpendicular. So I know that seems very complicated, but you're going to have to get used to it. That's just, that's just math courses. Sometimes you have to do very complicated problems. So we're going to start with angle 3 is a right angle, and that's given. That means that the measure of angle 3 must be 90 degrees. And that's just the definition of a right angle. Now we know that the measure of angle 3 is equal to the measure of angle 2 by the Vertical Angles Theorem. Now notice that I skipped right down to the measures. The Vertical Angles Theorem, the way that we stated it, we said that vertical angles are congruent. I'm just going to skip right down to the measures are equal. Sometimes it's okay to skip small steps like that. You're going to see proofs in textbooks where they skip steps like that. If you showed every single step for a proof, then sometimes it just becomes very long and very tedious. So it's okay to sometimes skip little steps. So we know measure of angle 3 is equal to measure of angle 2 by the Vertical Angles Theorem. But look, these two numbers are both equal to the measure of angle 3. So that means that they're equal to each other. So measure of angle 2 must be equal to 90 degrees. And that's the transitive property of equality. Now we're told that the measure of angle ABC is equal to the measure of angle 2, and that's given information. You can read that up there. They told us that. So this number and this number are both equal to 2. So that means they must be equal to each other. So the measure of angle ABC must be equal to 90 degrees. And that's the transitive property of equality again. Now that means that if measure of ABC is 90 degrees, that means angle ABC is a right angle. That's just the definition of right angles. Now, if ABC is a right angle, then that means by definition the lines AB, remember that's the definition of perpendicular, AB must be perpendicular to BC. And remember, this is the symbol for perpendicular. And that is the definition of perpendicular lines. So that was the proof for that particular problem. Again, we're learning how to prove that two lines are perpendicular. Sometimes we prove that two segments are perpendicular or two rays are perpendicular. So now I'm going to leave that problem in the window, and I want you to do number 10. Now for number 10, I want you to be aware that in the actual sentence, the actual statement, it doesn't say that angle ABC is a right angle. But in the picture, you can see that little box there Remember, when you have a little box there, that means it's a right angle, and the measure is 90 degrees. So you can use that as part of the given information. Again, it doesn't say that in the sentence, it doesn't say that in the statement, but in the picture we see it's a right angle. So try number 10, and when you come back, we'll do it together. All right, we're back. We know the measure of ABC is equal to the measure of ADC. So these two measures are equal. These two measures are equal, and EDF is equal to EGF. So that means that this angle, EDF, is equal to this angle, EGF. And we have to show that EG and GF are perpendicular. So EG and GF we're going to show are perpendicular. So let's kind of work backwards here. So EG and GF we're trying to show they're perpendicular. In order to show that, we have to show that this angle is 90. Now, we know that this angle, EGF, is equal to EDF, this angle, because they told us that here. So if we want to prove that this angle is 90, we have to show that this angle is 90 because we know they're equal. And we're told we can find out that this angle is 90 and use the Vertical Angles Theorem to show that this angle is also 90. But of course we have to show that this angle is 90, but they give us that information. This angle, they tell us, is equal to this angle, and we know that this angle is a 90-degree angle. So again, I know that you're probably thinking, I don't want to do all that. That sounds really complicated, but you just have to give it your best shot. These are some harder proofs. So we'll start out with the given information, the information given in the picture. So angle ABC is a right angle, and that's given in the diagram. Now, that means the measure of angle ABC is equal to 90 degrees, and that's given. Actually, no, that's a definition, sorry. That's a definition of a right angle. Now, we know that the measure of angle ABC is equal to the measure of angle ADC. That's given. So we can now use the transitive property of equality to show that the measure of ADC is 90 degrees, because they're both equal to the measure of ABC. So now we can say 90 degrees is equal to measure of angle ADC by the transitive property of equality. All right, so we've proven that this angle is 90 degrees. Now, how do we prove that this angle is equal to this angle? Well, we're going to need the Vertical Angles Theorem. So we know that the measure of angle ADC is equal to the measure of angle EDF by the Vertical Angles Theorem. Now again, I kind of skipped there. I didn't say the actual Vertical Angles Theorem that we stated says that vertical angles are congruent. I'm just skipping right down to the measures are equal because I don't want this to get too tedious. So ADC is equal to EDF. And of course, we have two things that are both equal to ADC. So that proves that the measure of angle EDF is equal to 90 degrees. Transitive property of equality. All right, so now we've proven that this angle is 90 degrees. So now we have to use the other piece of given information up here. We are told that the measure of angle EDF is equal to the measure of angle EGF. And that is given information. So now again we're going to use a transitive property. So we have two things that are both equal to EDF, so they must be equal to themselves. Measure of angle EGF must be equal to 90 degrees. Transitive property of equality. And now, because we know that EGF is equal to 90 degrees, that's this angle up here is equal to 90 degrees. That means that, well, first of all, that means it's a right angle. So angle EGF is a right angle. That's the definition of right angles. And if EGF is a right angle, then by definition, EG, the segment EG, is perpendicular to the segment GF, or the side GF. You can call them segments or sides, whatever you want. And that is the definition of perpendicular. So again, that was kind of a challenge problem. We had to use the transitive property a lot, quite a few times, and if you got stuck, that's okay. Don't feel bad if you're getting stuck on these problems. It's normal to get stuck, but you have to understand the main concept, and you have to start to get to the point where you can do these on your own without help. So that was the class today. I want you to go ahead and take screenshots of all the work that we did so you can refer back to these notes when you're doing your homework or when you're studying for tests. Again, in these last problems, we learned how to show that two things are perpendicular. So now let's go to the homework. The good news is I didn't give you a lot of problems for your homework, only 8 problems, I believe. So get a screenshot of that. And get a screenshot of this page. And don't forget to get the answers. You need to check all of your answers. It's not enough for you to attempt the homework. You have to do it correctly, completely, and neatly. And most importantly, you have to know where your homework is, and it has to be in the proper order. So remember, if you don't do the homework, it's a 100% guarantee that you're going to learn nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.